Welcome to LIB Academy, and in this video we are going to derive energy and momentum operators from the idea of classical mechanics. So to start with, the description of periodic forces. What are periodic forces? A periodic force is that its magnitude and direction repeat at constant regular time interval, or any push or pull that repeat itself at regular intervals of time. And this force drives an object to repeat its path or motion over and over in a fixed amount of time. The example of devices that exhibit periodic forces are the swinging pendulum and the mass on string. When you pull it and leave it, and the Earth in its orbit around the Sun too, they also exhibit periodic forces. A swinging pendulum under the influence of gravity, which causes the forward and back movement at a fixed time interval. A bouncing mass on a string exhibit all these exhibit periodic forces. So that is basically the definition of periodic forces, or what a periodic force is. So now that we know what a periodic force is, why are we starting from periodic forces? The description of periodic forces. Periodic motions arising from forces that occur in nature has attributes of a wave, described by a classical mechanics equation for a traveling wave as, let's say, psi xt equal I kw minus wt to bracket, omega right here. So according to classical mechanics, this is a mathematical model that describes a classical wave, right? So we believe that these periodic forces causes vibration in object, and we are trying to study, the periodic forces causes disturbances in systems that are more like waves, and we are trying to study them and see how far we can go with these properties. So according to classical physics, a traveling wave, this is a mathematical model equation that describes a traveling wave. So where we have our k, which is the wave number, k, the wave number should be equal to 2 pi over lambda. And we also have angular frequency which is omega, to be 2 pi v velocity. So I just want to introduce us to where we are coming from, the basic idea from classical mechanics, before we make the quantum deductions. So for now, we can just keep, these equations away, but you should know why we are stating these equations by the end of this video. So now, Schrödinger took as his starting point a fundamental equation for a wave traveling in the x direction for an electromagnetic wave traveling in a vacuum with a velocity c. So, and this equation was represented for an electromagnetic wave. This is the Azerian equations that describe an electromagnetic wave. And you might be wondering, what is the difference? The difference between classical wave and an electromagnetic wave. So, in simple terms, an electromagnetic wave, classical wave, an electromagnetic wave is a specific type of classical wave. Let me elaborate on this a little bit. So we have periodic forces, and giving us the disturbance from periodic forces, giving us classical waves, and from classical waves, a specific type of classical wave. A classical wave is the electromagnetic wave. So now let's look at what a classical wave is and what an electromagnetic wave is. Because these waves, the mathematical model that describes them looks similar. It has the same general structure, general formula structure. So the classical wave is the general mathematical description of a wave, the classical wave formula, which was here. This formula is the general description of a classical wave. And we also have a general formula that describes um, an electromagnetic wave. Let me write that down here. This is kx minus, this should rather be kx omega t. Here, classical wave equation, and here, electromagnetic wave equation, right? And their differential form also has, the same structure. So for an electromagnetic wave, the differential is also of this form, the electric field. So I'm writing it in terms of how they call it, the electric field. And this one, I already said that this one is a differential, form of the electromagnetic wave. Yes, and it is true. Just that for a classical wave, this should be V. You can write this as the same. You can write this as an equation that describes an electromagnetic wave, but this should be the term here should be c. The speed of light, not the normal velocity. The moment the velocity comes in, then it becomes a classical wave model. But what we are trying to see here is that, looking at this is a classical wave and this is an electromagnetic wave. They do have the same general formula structure. If you look at this and that, the same general formula, their differential form is also actually the same. So, in simple terms, classical traveling wave equation is a general mathematical description of any wave moving through space, right? Or any disturbances that transfer energy through a medium. An electromagnetic wave is in a vacuum is a specific physical wave made of an electric and magnetic field, right? We wrote this in terms of an electric field. We can also write it in terms of magnetic field. So the key thing that we should take here is that, looking at the classical wave and the electromagnetic wave, they do have the same general formula. general formula structure. So their solution should have the same general structure too. But before that, let me talk a little bit on about electromagnetic wave. This wave was theoretically, predicted by Maxwell. So, and this wave is normally high speed object, right? Dealing with high speed objects such as light, I mean, high, high speed systems such as light, I mean, light, radio waves. That is why we have the term here to be at the speed of light. And here is normally dealing with um, that wavy substance that we experience on water bodies, or like water on air, water or air. So that is why we are dealing with velocity here. So one thing you should know here is that these equations are just model. We are trying to explain matter a little bit further aside the classical realm. So now let's start our main business now. So as I was saying, so this equation was actually derived from, Maxwell's relation. But Hertz was the one who verified, I mean, Heinrich Hertz experimentally produced and detected radio waves in the 1880s, confirming Maxwell's prediction. Schrodinger was looking at the differential form of this equation describing waves, right? And the reason why we were looking for these terms is that they are very important to us in this lesson. So we got to realize that either the electromagnetic or the classical um, mathematical model of waves, they do have the same general structure. And their solution were found to be this. Let me write this general term here. So because for an electromagnetic wave, we have a differential form to be, we don't want to be using E here for the electric field because the two equations has the same structure. We want to use X and Y because in our term we'll be having E as energy, right? So we don't want to introduce another E which might make dealing with variables be somehow confusing. So in this case, Y is the displacement in the x-axis. X direction. Where C is the velocity here to be the speed of light, velocity of light. So Schrodinger take this, he took this equation, this electromagnetic equation, the differential form, replace the Y here, the displacement here, by the wave function psi. The wave function psi. So he replaced Y. Wherever we see Y, we replace it by psi here. Psi. D squared over dx squared. That's what it is. Equal 1 over c squared d squared over dt squared. And we have Y here replaced by psi. y here psi. So this is where Schrodinger started his prediction, where the wave function, psi xt, is a function that describes the behavior, the behavior of an electron, and is a function of, distance, x, and then time t, right? It's a function of distance x here and time t here. So a solution of the general wave equation that we were describing here, is of very important to us. And the general solution for this wave equation, because they have the same structure, we are talking about an electromagnetic wave here. The general solution for an electromagnetic wave is CIA. So because they have the same structure, the general solution of electromagnetic wave is this, and that of classical wave too, a traveling classical wave too, also have the same general solution as this. So this is why we were looking at those equations. So we are now going to stand on this equation to do our major business. So you can keep this wave equation in your head, and this is the general solution of an electromagnetic wave. General mathematical model that describes an electromagnetic wave. It could be a classical wave. So this is the general equation where C is a constant, and then I equal root of -1, square root of -1, and alpha is the phase. This one, let's make it alpha. Alpha is the phase, the phase, which is equal to 2 pi into bracket x over lambda minus vt. So this function, we can just call it the wave function. So if we say the wave function, if we mention wave function, then this is what we are referring to. And it can be split into two factors. So now let's take our work here very serious. Remember, we said that this wave function describes the behavior of an electron, and is a function of distance x. So x here is talking about distance, and t here is talking about time. And we know the value of our alpha right here, right? So we can just put the value of alpha there. So we will have a wave equation psi x of t to be equal to c e I, and we know our alpha to be 2 pi. So 2 pi into bracket x over lambda minus vt, right? So let's try expanding this exponent. We multiply this by that and multiply this by that. So we are going to get c e to the power. So I 2 pi multiplied by x on lambda. So I 2 pi multiplied by x on lambda. Just get xn over lambda. And then I 2 pi multiplied by minus vt. That should give us I 2 pi vt. And from our basic mathematics, we know that if we have e to the exponent a minus b is the same as e to the power a multiply e to the power minus b, right? Minus b here and a here. So let's do it that way. So we are going to get c e to the power this, which is I 2 pi x over lambda, and then e to the power minus I 2 pi vt. So now our wave function is now splitted into two parts. We are looking at a wave function with distance factor x and time t. So this is separated into the distance part and then the time part. We can also write this as to be equals to x. This is actually x, e to the power minus 2 pi vt, where this function here is a function of x but not of t. Why are we calling it a function of x? It's basically this. We are replacing this by psi x as the distance part, right? And this one too is that of time part. So if we bring psi x here, it means a whole of this thing here. And this two, we can replace this with psi t. So far, just know that we can also write this equation in this form. I mean, this equation right here in this form. So now what we are going to do is to introduce the Broglie, the Broglie and then Planck relation. So Planck-Einstein relation is E equal hv, and let's make v the subject. So v equal E on h. This equation here. This is the Planck-Einstein relation, where E is the energy and h is the Planck constant. And let's look at that of the Broglie relation. The Broglie's relation is lambda equal h over px, where px is the momentum in x direction. So what we want to do now is to replace our omega, our lambda here by h over px, and then our v here by e over h. So let's go ahead and do that. Let's work it somewhere and replace it. So we have I 2 pi x, and now our lambda, we are going to replace it by h over px, right? So let's have our h over px. Let's divide it here. H over px means dividing the whole of this. So taking the reciprocal of this, p will go up and then h will come down, right? So this is basically going to be 2 pi x multiplied by px over h. So which will be getting I 2 pi x multiplied by px. We have px here, all divided by h. Since it's multiplication, we can just bring h here. So that is it for the lambda part. Let's see how our v part is going to be. We have minus I here. So minus I 2 pi vt, right? So we are going to replace v by e over h. So minus I 2 pi v should be e over ht, right? We can just rearrange this as minus I 2 pi and then t here and then e there. Since they are multiplying, we can just divide the whole term here by h. So now we are going to replace this whole term here at the exponential part. So now let's continue. You can actually pause and write. Now we are going to write a wave equation as, or the wave function as psi h of t to be c. So now we know this whole term here after replacing the, doing substituting the value of lambda here. This is what we got. So we are going to write e to the power all of this minus I 2 pi x p x all on h here. And for this one too here, we are going to, this term here, after we did our substitution, this is what we got. So we are going to have e to the power minus I 2 pi t e all on h. So now, like we said earlier, we are going to stand on this equation again and differentiate it with respect to time and see what we get. After that, we differentiate it with respect to x and see what we will get. Two matter equations. The first one was the general solution of electromagnetic wave, followed by defining the wave function, which was right here, the general solution of the wave. And then we got here to define the wave function. And here we have introduced the Planck and then Einstein-Planck's relation and the Broglie relation into the equation to get another one here. We are going to stand on this, divide it, differentiate it with respect to time and with respect to distance and see what we will get. So now let's take we are differentiating the wave function with respect to time. So d psi xt all of dt. So what are we going to get? If we differentiate this whole term here with respect to t, what do we get? Well, we are going to look at where we have our time variable, because that is basically what we are going to do here. So this is where we have our time variable. Here we don't have any time variable there, right? So we can just write the same thing. C, we don't have the same, time variable here on this e to the power I 2 pi x p x over h. So we just write it as it is. So I 2 pi x p x slash h. So now this is where we are going to do the differentiation. And we have t component here. So if we differentiate this t here, we are going to get 1. So the power multiplied by this and it will reduce by 1. We are going to get 1, right? Okay. So exponential differentiation. If we are to differentiate e to the power u, first of all, what we do is we multiply e to the power u by the derivative of u, right? So in this case, this is what we want to differentiate. So this is now our u. What is the derivative of our u? We have our u to be minus I 2 pi te all on h, right? If we differentiate this u with respect to t, in this case we are differentiating with respect to t. So differentiating this with respect to t, what do we get? We differentiate only t, remaining 1. So we are going to get minus I 2 pi e. Because after we differentiate this term, we get 1 all on h. So in this case, this is our u. We are going to multiply u by the whole term. So we have a term here which will be minus I 2 pi e all on h, multiplying the whole exponential term here, which is e to the power I 2 pi t e over h. Mind you, we could multiply it at anywhere. Since they are multiplying, you can arrange them anyhow. But firstly, I know that because we are differentiating with respect to time, we don't have time term here. Definitely, we are going to write that one there, and the constant is a constant. We just have to write it there too, and then we now focus on where we have our variable, right? Differentiating this, what we do is that we multiply the derivative of this. We find the derivative of this and multiply it by all of this, as indicated here. So we are differentiating e to the power u. So we find the derivative of u, which we found it to be this, multiplied by e to the power u, which is here e to the power u. So now let's continue. This is the result when we differentiate with respect to time. This is our result. Now, what do you see? I wish you could see that c e to the power I to pi x px over h. We have it here. And minus I2 pi te all on h, we also have it here. And this c e to the power this, e to the power this, we call it as the wave function psi here. So it means we can therefore go ahead and represent this whole thing by the wave function. So 2 pi e all on h, it should be minus multiplying psi x of t, because this term here is the same as, this term right here is the same as the wave function. So we can just replace the wave function there. So our final solution for differentiating the equation, with respect to x, with respect to time, so d psi xt dt equal minus I 2 pi e all on h psi xt. This is our result. This equation is of great importance to us. Let's try rearranging this equation. Let's try to rearrange this equation in a form of let's say h psi equal e psi, in the form of our eigenvalue equation idea. So let's try that and see. So doing so, we want energy to be here with the function that we are dealing with, like this. So let's try doing that. So initially we can multiply by h. If we multiply through by h, let's say h multiplied by d dx of t, dt, going to get something like h multiplied by minus I 2 pi e right there, all on h, and the wave function x t. So this is going to take care of that, and we have h term here. So I mean we are going to get h d over dt, and write it this way, psi x t equal minus I 2 pi e. So since we are trying to rearrange it in this form, we want e term and the function to be there alone. So let's divide everything by minus I 2 pi. So if we divide both sides of the equation with this, by this, minus I 2 pi. So this is going to take care of that. So we are going to get something like h. So let's say minus, this minus sign will affect everything here. So minus h over I 2 pi, and then remaining d over dt psi x t should be equal to e that. So now we said earlier that this from the Planck-Einstein relation that this is the energy. I mean, this is energy, right? This E here is the energy of the system. So you could see that from eigenvalue equation, we said that if we operate an energy operator on a function, we get the energy and the function. That was our assumption from eigenfunctions, right? Yeah. So eigenfunction, because that the eigen means the same. You operate something on a red, substance, and at the end you get the red substance back and a certain value. So this is an energy operator. We can now define our energy operator as minus h over I 2 pi d dt. So after we differentiate with respect to t, after we differentiate the wave function with respect to t, what we were able to derive is the energy operator. Why energy operator? Because this was the final result that we got. We rearranged it in the eigenvalue equation form, and this is what we get. So looking at this, you see we have an operator here that is operated on a function to give us a value in the same function again. So this, we predict this as to be our energy operator. So this is actually our energy operator in quantum mechanics. So now let's differentiate the same equation with respect to x and see what happens. So keep this in mind. Where is our mother equation? This is our mother equation. So let's differentiate it with our mother equation right here, with x for now. So before we continue, differentiating with t time t, differentiating this with, equation with respect to time, what we get is the linear energy operator, or just call it as energy operator. So energy operator, very important to keep in mind. So now let's differentiate this with respect to x. After that, we rearrange in the eigenvalue equation form to see what happens. So we have to differentiate with respect to x. We are going to take d, the function, with respect to x. So it means we are going to focus on wherever we have the term x, right? So here we don't have a term x, we just write it as it is, and we have a constant here, we just write it as it is. So now let's focus on where we have the x term. We differentiate this term, and we multiply by the whole thing. So after we differentiate this, if we differentiate it, what do we get? We are going to focus on x. Differentiating x will give us 1, right? So it means we are just going to write this term here, which is I 2 pi px all on h. So now what is left? We have c there. We don't have x term here. We just write it as it is. So minus I 2 pi t e slash h. But don't forget that after we differentiate the exponent, we multiply it by the whole of this. So let's bring it there. I'm trying to arrange it in an order. So this will be I 2 pi x px slash h. And then again, if you look at this whole term here, it's still our wave function. C e to the power that which is here, e to the power negative 2 pi, that which is here. So this whole term, you can write it as a wave function, px, and then psi ht. So this is equal to differentiating the wave function with respect to x. So at this point, let's try and rearrange it in our eigenvalue equation form. We are trying to rearrange it in this form. So let's say, assuming like we are just trying to arrange it in this order. So now it means if we look at the terms here from the previous, formula, when we're differentiating, when we're rearranging with the energy E, we're trying to arrange them to leave the energy at the other side, E at the other side. Yeah. But now we are trying to arrange it in terms of momentum, rearrange in terms of momentum. Don't forget to divide this side by h. So it means if we multiply both sides of the equation by h will cancel, h and h here. We have a h term here, Okay, let's do it this way. H term here, and then xt all over dx I 2 pi px, and then the wave function xt. Right. So we divide with I 2 pi to leave only the momentum term. So after we do that, we are going to get h all on I 2 pi d, the wave function here, all on dx equal to px right here, and our wave function again. So it means that we operated something on the wave function, and we've gotten the value of that thing plus the wave function again. So we can now define a linear momentum operator. Now let me write the final equation very well. We have h all on I 2 pi d dx. We have the wave function here, and you have px here, and then the wave function. I hope you get me. From eigenvalue equations, I think this video is also part of the playlist. Eigenvalue equations, I have a video on that too. If you are not getting it, you can feel free to have an idea on eigenvalue equation, which will make things easier. But what an eigenvalue equation is, that it means you operate something, that if you operate something on the wave function, you get a value and the wave function at the end. It means the value that you get will be the operator that you operated on the wave function here. This right here is an operator acting on the wave function to give us the wave function back and the value. So if this is energy, this is an energy operator, if you operate it on the wave function, you get the value of the energy here and the wave function back. If it is a linear momentum operator, if you operate it on the wave function, you get the value of the energy here and the wave function. So if it is let's say a velocity operator, assuming a velocity operator, if you operate on the wave function, you get the value of the velocity and then a wave function back. But don't forget, we are just predicting. So at the end of the day, we can now say that our linear momentum operator equal to the whole of this right here. So h all on I 2 pi d over dx. This is our energy operator. So what do you see? For the energy operator, if we differentiate the wave equation with respect to time, we get the energy operator, which is minus h over I 2 pi d dt. But if we differentiate the wave equation with respect to x, which is the distance x, we get h over I 2 pi d dx. So it's just the same, But you should know that differentiating with time gives you this, differentiating with x gives you this. And more importantly, you should know the mother equation. I mean, the wave equation, the wave function after we substitute the Einstein-Planck's relation and then the Broglie's relation. That is it for this video. Thank you for watching. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.